I think we're all set to go with the broadcast here. So, ladies and gentlemen, today we're going to be continuing on a bit more coverage of this key building block of system dynamics models that's known as a first-order delay. This is I've mentioned before that system dynamics models are composed out of three major pieces and some supporting pieces: stocks, flows into and out of said stocks, and finally constants. There's a supporting piece of machinery called the dynamic variable or auxiliary variable, which might be the sum, for example, of several stocks. This variable is used as sort of a convenience to keep track of values of mathematical expressions involving stocks, flows, and constants. Within system dynamics, though, more broadly, we have these pieces at the most basic level, but the next level up, the most basic piece, is this construct called a first-order delay. And as part of your assignment, you worked with a number of first-order delays, and we saw them in some detail last time. So this is an example of a first-order delay. Here we have a population, say, and there's a certain hazard rate, a certain chance per unit time, continuously applied. Here it's phrased as a mortality rate. And the formula for the outflow depends linearly on the value of the stock. When I say linearly, it's just some constant, in this case the mortality rate, times the value of the stock, alpha times population. This is a system which is linear in terms of the stock, and we can phrase it in one of two ways. One way we can phrase it is in terms of a mortality rate, a hazard rate of proceeding. The other way we can deal with it, we could phrase it, is in terms of a mean time in that stock. They're interchangeable ways. Alpha, the hazard rate, is just 1 over the mean time in the stock, here shown as tau. And in this case, it's alpha times the population for this flow. In this other case, where we have mean lifetime, it's population divided by tau. That has to be the case, ladies and gentlemen, for reasons that I'll talk about. And this has deeper implications we'll be talking about later in the class. Suppose we have a stock. For fairness, I'll do it over on this board. Suppose we have a stock population, we'll call it X more generically, and we have a flow into or out of the stock. Suppose the stock is in terms of a certain number of units. Maybe it's liters, okay? This is a stock of the bathtub, and it has a certain number of liters of water in it. So suppose there's 50 liters of water within this stock, okay? The unit, that specifies the unit by which we measure the value of the stock. It's in liters. So if we have 50, we know it means 50 liters, not 50 gallons or 50 microliters or 50 nanoliters or what have you. We have a unit associated with the stock. It tells us according to what meter stick are we measuring that value. It's 50 watt. So if it has the value 50, that's all nice and good, but we want to know 50 watt. 50 feet, 50 meters, 50 liters. It has a certain unit associated with it. It has a dimension, which is sort of what sort of thing is it? In this case, it's a volume. And it has a unit by which we measure that dimension. In this case, liters rather than gallons, or rather than cubic meters or something like that. So when we have these models, they model characteristic things in the world, and things in the world have certain semantic types. They have certain dimensions that apply to them. I talk about yay long, that's a length. I talk about the amount of water in a bathtub, that's That's a volume metric. So when we think about quantities in the world, it's typically extraordinarily useful, and it turns out extraordinarily powerful to think of them as having units. Much as in your programming languages, you have types, right? And much as in your programming language, it doesn't make sense to add, a float to a pointer to a character, or to add a double directly to a hash table or to a string. So it is with units. We need to be careful with our units for describing things. So suppose here we have a bathtub and we characterize its units in liters. Or suppose we have a population, we characterize its units as count of persons in that population. What are the units associated with the flows into or out of that stock? What sort of things are they? Think about it. Yes. It's units per time unit. So maybe I have a time unit by which I measure time in the model of weeks. Or maybe it's days. Maybe it's hours. Maybe it's years. Centuries. I could say I'm going to use that unit of time, and if I see a 1 in the model in terms of time, I know it's 1 year. Or in this other model, I know it's 1 second. So I have a unit associated with time. And if we have a stock whose unit is some unit T, I'll call it unit U, just it's not necessarily a type, unit U, and we have a flow into that stock, its unit, I'll write it like this. I'll write it in sort of brackets like this. The unit associated with X, and putting it in square brackets is U. The unit associated with the flow into or out of that stock is U over some unit of time. Years, seconds, centuries, okay? That has to be the case. Now, why is this relevant here? Why am I making a big stink about it? Well, 2 reasons. So first of all, I'm prepping you for some stuff later in the course where we can really use this. We can use it to reduce the number of parameters in our model. We can use it to do sensitivity analyses or calibration in a much more savvy way. But the other reason I'm using it is because it prevents a common student error on exams. It'll prevent you from making a mistake in the exam if you think clearly about it. Ladies and gentlemen, I'll start with the simple one. Mean lifetime. What are the units associated with that? Units of time. Thank you. Units of time. Mean lifetime. Who knows what it is? 50.2, 33.6, 88.9. But the point is it has a unit associated with it. Years, let's say. And you'll notice what the formula is for the outflow here. If this mean lifetime, tau, has a certain unit, let's say, of years, and let's say the population has a unit of people, count of people, then what is the unit associated with this flow of death? If the formula for the flow, for death here, is population divided by tau, what's the unit associated with that? Yeah, person per unit time, in this case, year. Okay? We say time is the dimension of tau. We say the unit of tau is year, or we'd say it's second or microsecond or what have you. So the unit of it is year, and so the formula given for death implies a unit for this flow of persons per unit time or year, right? Does that make sense? Ladies and gentlemen, does that make sense? Okay. And that checks with what we need, right? If we have a stock, and it has units U, the flows into an outer stock have to have units what? Units U over time. Good man. U over time. And that's what this is, right? This has units. Population divided by tau has units. The units of population, people, over the units of tau. Time, in this case, years. So it's people per year. So it has the right dimension. It has the right units to be meaningful. The right dimension, right? It is dimension, whatever the stock is divided by time. It has to be the case because the stock integrates the flow. It accumulates it over time. So its units will be whatever the units of the flow are times time. Or conversely, the flow, the net flow, the sum of all the flows is just the derivative of the stock, d population dt. And that is units d population, which is people, divided by dt. dt is units time. So it has to be the case. Do you have an understanding of that? So if we have a bathtub, we have 50 liters in the bathtub, and the water is coming in at 10 liters a second, and it's leaving at 5 liters a second. The point is that those flows have whatever the dimension is and whatever the unit is associated with the stock divided by the dimension or unit, respectively, associated with time. Does that make sense? Okay, now, this is what I'm trying to give you this so that I don't feel bad in a few months' time when I'm correcting your exam and you make a needless mistake. So, ladies and gentlemen, never think that if you have a mean lifetime that the formula is population times time. It does not make sense dimensionally. It doesn't make sense for the stock to have a dimension of people in the flow to have a dimension of people times time. No, the flow has to have dimension, whatever it is of the stock divided by time, divided by the unit of time. Do you appreciate that issue? Okay, because every year I get students who make that mistake. Now, let me ask you this. Mortality rate here, hazard rate, it's a probability per unit time. What is its dimension? What is its, what are its units? Let's talk in terms of units and talk about years. What are its units? Okay, mortality rate. So this is going to be a chance, a probability per unit time is, so it's like your probability of dying in the next day. What are the units associated with that? I welcome suggestions. Is it, okay, what are the units associated with the flow? What does it have to be? If you have a stock, the flow has to have the units of the stock divided by time. Okay. The formula for the stock is alpha times population. What are the units associated with this formula for death here? It's whatever units are associated with alpha times the units associated with the population, right? What are the units associated with the population? Person. What does that imply the units of alpha have to be? 1 over time. And you may think, what in the world is that? 1 over time. Well, I would argue, it's a perfectly good description of probability per unit time. The units associated with probability, ladies and gentlemen, the units associated with probability, we can think of it as asking, if we flip a coin, 100 times, what fraction come out heads, right? Say 50 over 100. Whatever it is, 40 over 100, 20 out of 100. Maybe the loon has a really heavy beak. Okay. But the point is, this is a count of coins, of coin flips that turned out heads divided by a count of coin flips. What's the unit of that? If I say, what's the fraction of this room that's covered by these things, what's the unit associated with that? I'm going to ask you a trick question. If I want to quantify the floor area of this room as a whole, how might I measure that? Give me one unit in which I can measure that. Well, okay. I heard. Welcome the Greek chorus. What? Give me one. Square meters, right? Square meters. Or I could quantify it in square feet, couldn't I? I could quantify it in square miles. Those with an acreage could quantify in terms of sections, right? This room occupies 0.0001 section length, right? I could quantify the floor area. But now if I ask, what's the fraction of the floor area covered by these desks? What's the unit associated with that? It's dimensionless. What does that mean, dimensionless? Yeah, it's a ratio of the dimension of itself. So does it matter? Let's suppose that someone were to tell me, let's suppose that, yeah, you'd like to see this. Let's suppose that I tell you, by my calculation, I prefer to think in terms of square feet. And the fraction of this room that's covered by these desks is 0.5. It's half the room. Half the room. Now suppose an alien were to come in. Okay? And that alien has a totally different system of units. They talk in terms of whatever their unit is. If you were to ask the alien what fraction of this room is covered by desks, would they give? Is it possible their unit system would apply a different unit? No. It turns out it doesn't matter whether I prefer to call it in terms of the unit, the area of the whole room, in terms of square feet or square meters. The fraction occupied by these things is the same, because it's whatever the dimension is on the top divided by that same dimension at the bottom. However many square feet are occupied by these desks divided by the number of square feet in the whole room. It cancels. The unit cancels. Alternatively, I could measure the number of square feet or number of square meters occupied by these things divided by the number of square meters in the whole room. They cancel in both cases. It's going to give me 0.5, whether I quantify it in one system or another. It's invariant of units. It doesn't matter what units I have, what units I choose to use. Do you get that point? And same thing with fraction of coin flips that turn up heads. Doesn't matter if I count coin flips one at a time or 1,000. One means 1,000 of them. It's an invariant measure. It's a fraction of it. And the units in the numerator and denominator are the same. They cancel. So ladies and gentlemen, a probability is dimensionless. It has unit dimension. It does not change. The value of it does not change if you use one unit system or another. That statement is going to come back to us in a big way, in a profound way, many lectures hence. Dimensionless quantities are invariant of units. It doesn't matter what unit system we have. The value of them will not change. They are independent of our unit systems. And it turns out we can always describe processes in the world, and processes involving people or other factors, in dimensionless terms. Because the world doesn't care about it. Ponder that, those of you who are interested in going further. Okay, so probabilities are dimensionless quantities. So when I say mortality rate is a probability per unit time, what is its dimension? Its dimension is 1 over time. Its units are 1 over the units of time. It's a chance per unit time, a probability per unit time. And therefore, we call things with unit dimension things that are dimensionless dimension 1, and we put it over the amount of time here. So mortality rate has dimension 1 over time. A fraction would just have dimension 1. The numerator and denominator cancels, so it gives 1. So mortality rate here is dimension 1 over time. We multiply it times the population, which is dimension common people, and we get something whose units are people divided by time. So we can phrase a first order delay in short, using either this, with mortality rate being of unit 1 over time, my probability per day of getting sick, or dying, or we can phrase it in terms of, and in that case, if we're dealing with a hazard rate, the formula for the outflow is the hazard rate times the size of the population, right? It has to be the case. It can't be population divided by tau. It would be the wrong units. If you put down population divided by tau, it gives the wrong units. It would imply the units associated with death or person times time, which doesn't make sense. It has to be the case that it's alpha times population for the dimensionally to make sense. And similarly here, it has to be the case the formula is population divided by tau. And I would argue these two framings, these two phrasings, these two characterizations, these two representations of a first order delay are interchangeable. The value of tau, how is the value of tau related to the value of alpha? Anyone? Okay, opposite in what sense? That's absolutely cool. It's what? Yeah, it's 1 over it. One's the reciprocal of the other. That's all it is. Ladies and gentlemen, what that means. I'm going to burn out my throat. The folks out in the lab, they're getting a lesson too in dimensions. Let's see how many of them haven't fled by the end. Ladies and gentlemen, what that implies is that the mean time in that stock here is just 1 over the hazard rate of leaving that stock, and vice versa. Or it's proportional to that. We actually have a proof later that it's in fact exactly that alpha equals 1 over tau, or you could phrase it as tau equals 1 over alpha. And the dimensions all make sense. Alpha is a dimension 1 over time. You take 1 over alpha, and it's dimension time. And that's exactly what this is. Or, alternatively, alpha equals 1 over tau, because the units of alpha are 1 over the units of tau. Sinking in? Okay. Okay, I'm glad. Otherwise, my throat would be in trouble. Okay. Now, beyond these niceties involving dimension, this type of first order delay has goal-seeking behavior, right? The larger the population is in the stock, the bigger will that be the value of the population divided by tau, by a constant, or the larger the value of population times alpha, right? The larger the value of the stock, the faster people will be coming out of this stock, right? And the smaller the value of the stock, the smaller number of people come out of the stock. If the population is 0, what's the rate of flow out of the stock? 0. 0, ladies and gentlemen. And that's associated with a goal-seeking behavior. The stock wants to come back to some natural value of flow. What is, if we have this inflow, into the stock, here immigration, and we have a stock that's way out of whack, it's way bigger than its equilibrium value, what value will it want to come back to? Oh. For once, there's more energy outside the room than there is inside. Couldn't invite him into the lecture. Okay, so ladies and gentlemen, if this stock has a huge value, it's out of whack, it's out of balance. It has a huge value, and deaths are just occurring at a very high rate. What's the value of death to which this stock wants to come back? When will it be in balance? When inflow equals outflow. That's when it's in balance. That's when it's not changing by definition, right? If the stock is way below its normal level, the outflow will be very small and it will rise, right? So in short, there's kind of this gap between the rate of inflow and the rate of outflow. The bigger the rate of outflow is, the bigger or sort of bigger the inflow is, the bigger the surplus will be over a given level of outflow. That increases the value of the stock, which increases the rate of outflow, which lowers the gap, right? This is how the stock stays in balance. And inflow sort of sets the target for the outflow. If inflow is out of balance, the stock will adjust. That's why it's a balancing loop. Do you appreciate that issue? I'm not asking do you like it, but do you appreciate it in the sense do you grok it? Grok or not? Okay, grok. Okay, excellent. I like grok. Okay. And actually I do appreciate it. Okay. Okay. Ladies and gentlemen, we talked about how this stock and flow is associated actually with some underlying mathematics. And last time I introduced this to talk about the fact I asked, okay, to think through this notion that you have a certain chance per unit time of leaving the stock. Not just once, but no matter how finely you look, you have a certain chance of leaving in the next little bit. I made an argument to sort of say, suppose we had one chance of only leaving it between time 0 and t. What would be our chance of leaving? Now suppose we had 2, suppose we had 3, now suppose we had n. And I argued that if we let n go up, what it implies, we have n go to infinity, implies that the value of the stock decreases over time as e to the minus alpha t, exponent of alpha times t with a minus sign up front. So what that means is the stock will drop, and the stock will drop faster at first. Do you remember this? And then it will drop slower later. Why does it drop faster at first? I want to make sure these intuitions are rock solid. Yeah, the population is very high, so there's lots of people dying, so the rate of dying, people per unit time, is very high. And so as a result, the population drops very quickly, fast. Later on, why does it drop very slowly? Because not many people left to die. So the rate of outflow is very, very small. The rate of deaths will be going down like this as well, because it's just proportional to the value of the population, right? It's just alpha times the value of the population. Alpha is some constant. And so if the population is going down, the rate of death and people per unit time is going down. Let me just as a sanity check here. As we view this, the number of people in the stock going down like that, is alpha changing over time? No, alpha is constant. Conditional on still being in the stock. If you're in the stock, the model has just started, you're a person in the stock, what chance do you have per unit time of leaving, say per year? Alpha, well, continuously compounded. If I've been there 10 months, what chance do I, okay, so let me phrase it more clearly. If I'm just at the stock at the beginning, what's my chance of dying in the next month? It's some number, right? If I've been there 10 months, if I'm still there in the stock, what's my chance of dying in the next month? Same number. If I've been there 100 months, what's my chance of dying in the next month? Same number. Alpha is a fixed quantity, and the system is memoryless, meaning it doesn't matter how long you've been in here. We consider, as we say, well mixed. Your chance of leaving the next little time unit is alpha. Alpha. Sometimes you even clap out of appreciation for it. Okay. Ladies and gentlemen, so what we have here, we have a system whose rate of change of the stock X, whether it's going up or down, is proportional to minus alpha times X. That's actually, in fact, what this is telling us, because this is the state variable. This is the state variable here, x, and this is the derivative of it is the sum of immigration and death, okay? If we just have an outflow, if we only have an outflow, then the derivative of the population is population divided by tau. That's just, it's an outflow, so there's a minus up front, or minus alpha times the value of the stock. If we call the stock x, the rate of change of the stock, if we don't have an inflow, is just minus alpha times x. It's going down at rate alpha times x. Do you get that? Okay, so that's the rate of change of the stock here, okay? Now, let's suppose that we were to think about taking this forward step by step. What that's saying is how quickly the stock is going down changes over time. It's going down quickly at first, slowly later. Let's imagine we were to do what's called integration, which is really simulating a system dynamics model as a matter of integrating them, taking it step by step. We consider time 0. Let's consider a case where we have alpha equal 0.2 and x, the initial value of the stock being 1,000, and we're considering steps of time delta t, okay? I would say, okay, the value of the stock at first is 1,000, that's the initial value. And then what's the change of the stock over the next little delta t? Well, it's delta t, that's 1, times alpha, 0.2, times x, 1,000. So that's minus, and then a minus sign in front. So that's minus 200. You get that? Okay. So let's suppose now we consider time 1. So we jump forward from 0 to 1. At time 1, how many people are left in the stock? Where did that 800 come from? Whence did that come from? Yeah, 1,000 minus 200, right? 800, okay. Now, what would be the rate of change of the stock? Or sort of what is the change of stock over this time? Well, and to figure out the change of the stock over the next little delta t of 1 time unit, it's simply the stock value times alpha 0.2 times delta t, or 1, which would be minus 160. Where did that come from? 800 times 0.2 times 1, right? Okay, now the stock's going down between 1 and 2 by 160, and it's going down. Now we're at step 2. We have 640 people left. That's 800 minus 160, and we compute delta x for this period of time, this delta t, the next time unit, we get 128. We subtract it off and we get this. Okay, now you notice I say approximate there. Incidentally, we could compute the flow rate here, and the flow rate here is the same because it's delta x divided by delta t. Delta t is 1 here, so it's just the same values. Okay, why is this approximate? Why do I say it's approximate? What's so approximate about it? Why isn't it exact? If your step is smaller, you're going to get somewhat different numbers, okay? We're assuming here a step size of 1. And in so doing, we're assuming that the flow rate between time 0 and 1 stays constant for that entire period. It's staying constant at this flow rate of 200. That's why we're multiplying times delta t here. We're assuming this is the flow rate minus x times alpha. Remember, that's the rate of outflow of this is alpha times x. The rate of outflow is that. So the change in the stock is, or the rate of change is minus x times alpha. And we're assuming it applies over this entire delta t, this entire time unit here. But in fact, what's going on during that time unit between 0 and 1? Is the stock staying constant? Is it staying constant through this entire time unit? 0 to 1? No, it's not staying constant. It's dropping even during that time from 1,000 to 800. So ladies and gentlemen, here, in fact, it's a pretty crude approximation. Now, how can we do better? Well, we can use a smaller delta t. You appreciate that? Instead of doing 1, we can use 0.5, right? And here, we will get slightly different numbers. So the other one was telling us it would go from 1,000 to 800 by time 1. This is telling us actually That's not quite right. It's here, we use 0.5 as the step size. It goes to 810. Why? Because it's not decreasing as much as we thought in this guy here. Why did we think it was increasing more here? Or sorry, decreasing more. Why do we think it was a gap of 200 here? But here we're realizing a better approximation is 190. Why is this less than that other one? Yeah, we're dealing with half the time step at a time, and we realize that we don't have 1,000 people all through this interval, 0 to 1. We have 1,000 only. Here we're attributing to 0.5, and then we realize, okay, at that point it was 900. And so we attribute fewer people as having left during that time unit. Now, of course, we could go even further. We could do 0.25, and here we'll see that even this 810 is overstating how much it will decrease, right? Here it's 814 because we realize, wait, it's changing. And if you go and you plot it out, you'll see something like this. It converges. It converges to a well-defined sort of decrease. But, assuming time step 1 is pretty far off from assuming time step 0.5. But you see, as you increase it, as time steps become finer and finer, it converges towards a simple towards a solution that's consistent. And I want to introduce in here this notion of an analytic solution. The idea is here for certain problems, and this happens to be one of them. This one where we have a very simple linear system like this. Most of the systems, almost all the systems we're going to be looking at going forward, starting next lecture and onward, they're going to be nonlinear systems. But for a linear system like this, we have a delightful prospect of being able to do what's called solve it in closed form, meaning we can derive and write down a solution for it over time, like e to the minus alpha t. In general, with nonlinear systems, we don't have that option. We don't have a language for solving them. We don't have a way of solving them. The only thing we can do is simulate them. But here, for a linear system like this, we can. And we can take this system, which is known as a first order ordinary differential equation with constant coefficients, and we can solve it. And I'm not going to do this in gory detail, but it too is a thing of beauty. And basically you divide both sides by x, and you realize, okay, this guy is the derivative of the natural log of x, and this guy is the derivative of minus alpha times t, and you can solve it. And what you'll come out with is that this will decrease. If you go solve that by the principles of calculus, what you discover is that this will decrease as according to this formula, the initial value times e to the minus alpha t, which we saw before. So however much was in that stock at time 0, what will be left after time capital T? E to the minus alpha t will be remaining after that time. T could be 3.21. T could be 1021.2. Whatever it is, this is going to tell you how much is remaining. Okay? And that, indeed, is exactly what this was approximating. We were performing what's called numerical integration of this, and we're getting closer and closer to e to the minus alpha t. Okay? That's how it decreases, e to the minus alpha t. Now, you may wonder, why am I harping on this so much? Why am I harping on what's left? Because this is the fundamental building block to system dynamics models at a higher level is the first order delay. And if you have an intuition for how it operates by itself, it gives some understanding about how the whole model operates. Not because it's the same, it can't be directly reduced to it, but it gives you a feel for why you see certain results. Okay, you see that signature of it again and again, that fingerprint that it leaves. So the fraction of the stock that's left by time capital T is e to the minus alpha t. This is important enough I might test you on it. It's that important. And the fraction that have left by time t is 1 minus e to the alpha t. Okay, so these are the fundamental sort of mathematics associated with this. Okay, I think, I have in here a derivation that I consider quite beautiful. And basically what it derives is that the mean time, if you have the rate of leaving, the hazard rate is alpha. What's your average time in that stock? And it turns out to be exactly 1 over alpha. Your average time in the stock, 1 over alpha. So if I have a chance per year of 0.01 of dying, the average time I'll be alive is what? 100 years. 1 over 0.01. That's the average time I'll be alive. This is going to come back to us big time in a few weeks with agent-based models as well. Okay? Okay. Now, I'm going to explore some other aspects of this. Ladies and gentlemen, suppose we had a first-order delay, and we have an inflow to the delay that increases suddenly at time 50. Suppose the stock starts empty. By the way, I show this as increasing at time 50 for convenience, because the stock is empty. It helps communicate that. But we can just as easily deal with a model that starts with an inflow that's high. But here, the inflow at time 50 is going up to 20. I have a first order delay. The stock is initially empty. How does the outflow change over time? That's my question. How does the outflow change over time? Well, what we've just been talking about implies, going back here, that the fraction that have left by time t is given by this bottom expression here. Do you see that? See or not? 1 minus e to the alpha t, e to the minus alpha t. See that? That's the fraction that have left by time t. The fraction that remain is e to the minus alpha t. Fraction that have left is this. By the way, how would I remember that? This might seem like full of sound and fury, but you're confused. Why is it? How do I remember which is which? Whether it's 1 minus or that? Well, look, ladies and gentlemen, if I plug t equals 0 into this top one, e to the minus alpha t, what do I get as the value of that? Yeah, it's 1. It's e to the minus alpha times 0, or e to the minus 0, or e to the 0, or 1, right? That's 1. This is 1. So this has got to be the fraction of people that are still in the stock. And the fraction that have left by time 0 is 1 minus 1. That's e to the minus alpha t, which is 1, we just said. And so that's the fraction that have left by time 0 is 0. 1 minus 1 or 0, right? And then over time, more and more leave. And that's exactly what you see here. More and more leave. Ladies and gentlemen, if you wondered why this is called a first order delay, there's your delay. This output looks kind of like a delayed, sort of smeared version of this input. This input goes up at time 50 in a sharp way and continues at its higher value. The outflow follows it, but it follows it in kind of a smeared way. It's not as sharp. It follows it in kind of a gradual way. You see that? Okay, so that's what we call a first order delay. And if we were to deal, well, let me ask this. How would this change if you were to change alpha? How would it change if you were to change alpha? Let's suppose alpha is really, really, really long. How would this change? How would it change? How if alpha is really, really, really short?
Very small.
Ah, okay. So alpha really, really, really small. Do you think the delay will be small? That would mean I have a very low chance per unit time of leaving. Here's a view, and we will. So I welcome these suggestions. We'll try to show an example and build up a bit of intuition. So here we have a stock with a 2-year average delay. So this is tau being very short, or tau being short, very small, implies alpha being what? Very big, yeah. Bigger. By contrast, if we have tau being very big, it implies alpha is small, right? Remember, tau is 1 over alpha, or alpha is 1 over tau. So 20 years, for me to remain in this stock for 20 years on average would mean that my chance period time of leaving has to be pretty small per year. By contrast, if I'm going to leave this in 2 years on average, my chance of leaving per year is much bigger because I've got to have a kick in a can that I'll leave within 2 years. So here's a 2-year delay. And you could see that means it follows this increase in the inflow pretty quickly. By contrast, if I have a 20-year delay, that's the red one, it follows it more slowly.
So these numbers are not alpha.
Are not, these numbers are 1 over alpha. These numbers are tau.
Yeah.
That's why they're
The
here.
question was when alpha is big.
Yes. I'm trying to build up the intuition with this.
Okay.
And each of these implies an alpha.
So it's
Right?
the opposite, but sure.
It's the opposite.
Yeah.
So if alpha, yes, that's absolutely correct. So if alpha is very small, we'll have a long delay. It'll take someone a very long time to leave the stock. It'll take it a long time to adjust to the new value. By contrast, if alpha is quite large, in other words, tau is small, we'll adjust quite quickly to whatever new value we have, okay? So the stock has less inertia, okay? Conversely, we will see that that in fact we'll have different equilibria associated with this, okay? Here we go. Okay, now, when we have different lengths of delay, therefore, we get different sort of approximations to this. When we have a delay that's very short, it's a very rapid response. We have a delay that's very large, it's a slower response. Okay, now, what if the stock doesn't start empty? So if the stock started with values in it, while the flow is 0 into it, the first 50 units here, the stock will decay because there's no inflow into it. It'll decay. It'll decay at different rates according to tau. And then it will rebound accordingly. You'll notice, and this is very important, this was linked to the problem set that we talked about that you just finished. Ladies and gentlemen, the value of the stock that it achieves to be in equilibrium is quite different for different values of alpha or different values of tau. So we've been talking here about how the value of the outflow follows the value of the inflow. That's what this is about, right? How does the value of the outflow follow the value of the inflow? By contrast, if we want to think about what's the value of the stock, the value of the stock at some level follows the inflow, but it doesn't always go to the same value. So if I have a large value of tau, does the stock build up to a larger value or a smaller value? So suppose I have a value of tau of 20 years. Or I have a value of tau of 2 years. Which of them yields a higher equilibrium value of the stock? A value at which it's in balance for a given inflow. Yeah, 20 years is bigger because, I mean, you can think of it in several ways, but one thing is, at equilibrium, what is the key thing What is the key thing that distinguishes a stock that's in equilibrium? It's the fact that what? In equals outflow. That's what it needs to be in balance. And the outflow is the value of the stock divided by tau, right? So in order for the outflow, value of the stock divided by tau, to be equal to the inflow, if you have a bigger tau, you need a bigger value of the. Let's try that again. In order for the the outflow is the value of the stock divided by tau. In order, if we have a fixed inflow, a defined inflow, if we're dealing with a larger value of tau, so the outflow is the value of the stock divided by a larger value of tau. The value of the stock, does it need to be bigger or smaller to equal the same inflow? It needs to be bigger. It needs to make up for the bigger tau that's in the denominator. So if tau was 10 times as large as the denominator, the value of the stock needs to be 10 times larger. 10 times larger. It builds up to a higher level. That's because it doesn't turn over as quickly. You're in the stock for a longer time. 20 years in that darn stock. Imagine that. You think it's bad enough being in this class for 90 minutes. Imagine if you were trapped in the stock for 20 years. For some of us, it'll be a thing of delight, but not for all. Okay, ladies and gentlemen. So here we have stocks going to different values. The values of the outflows always are just a delayed version of the inflow. Because after all, the first order delay wants the outflow to approach the inflow, so it gets back in balance. The value of the stocks, though, for different values of tau or alpha turn out to be different things, such that the value of the outflow is the same. Okay, we're almost done with this. We're almost done with this, but there's a few things I want you to be able to further reason about. It's good we're almost done with this. My voice is almost done with. Okay. Okay. I don't want to get too excited about it. Okay, ladies and gentlemen, we can phrase a first order delay in one of two ways. We have been dealing here with one way of saying it, okay? So one way of framing it is we have a inflow and an outflow that are separate. The value of the stock we'll call X. The value of the outflow will be given by X divided by the delay, the mean time in the stock, right? Just been talking about this, right? And the inflow is some fixed thing. That stock, what does that stock want? What is that ladder, this bottom one, what does it want to make the case? What goal is it seeking? At what point will it be in balance, at rest, and what state is it seeking to get back to? A state where what equals what? Inflow equals outflow. It's trying to make this value of the outflow the same as the inflow. At that point, it'll be in balance, right? Good. Now, another equally good way to say this, though, to phrase the stock is as follows. Consider the same delay. We could frame the stock in this top one here, okay? So we have a flow into a stock. And the stock's goal here is to make the value of the stock, which I've called X2, equal to some target value. Okay? It's trying to minimize the difference between the stock and X target. And it does so by making the flow X target minus X2 divided by delay. So let me ask this. Suppose that the stock is a lot smaller than X target. What will be happening to the stock as a result? Okay, let me phrase this again. Suppose this X target is far above the value of X2. What will happen as a result? The stock will grow because X target minus X2 divided by delay, we're assuming delay is positive here, will be a pretty big value. And so there will be what into the stock? Inflow. That's pretty big. And that will raise the value of the stock. By raising the value of the stock, what impact will that have? It will lower this gap, right? It will lower this gap between X target and X2, because X2 is now getting bigger. So it's gonna lower that gap. This system is trying to minimize that gap, ladies and gentlemen. It's trying to minimize the gap between X target and X2. If X target is far above X2, X target minus X2 will be really big. Divided by the delay will be really big. It will have lots of value rushing into X2, and the value of X2 will go up quickly. Suppose X2 is just a little bit above, suppose X target is just a little bit above X2. X2 will be growing slowly. It'll rise slowly, right? It'll track the target more slowly. Suppose X target is a lot smaller, is much smaller than X2. What will happen? If X target is much smaller than X2, X target minus X2 will be a really big negative, a really large magnitude negative number, like minus 1,000. Right? Divided by the delay will be some big negative number, some large magnitude negative number, and that will lead to the stock being drained really quickly. What will happen as a result? The value of the stock will, so this is when X target, ladies and gentlemen, is much smaller than X2. So what will X2 do as a result of having very quick draining of it? Its value will go down towards the target, right? This is for the situation where the target is much smaller than X2, so it will chase the target. This top one is going to chase the target. It's a feedback system, similar to what we see in control theory. It's trying to chase the target. It's trying to minimize the difference between the target and X2, X target, X2. If the target is far above X2, X2 will rise as a result. If the target is much smaller than X2, X2 will drop quickly. If the target is a little bit smaller, X2 will drop slowly. If the target is a little bit bigger, X2 will rise slowly. Does that make sense? So this is another way to phrase it. Now, this way, this top way, well, the bottom way, I emphasized the system wants to seek here. Same system, just rephrased mathematically. System here wants to make the outflow equal to the inflow. That's its balance. That's where it's seeking. The top one, the system wants to make X2 be the same as target, and it adjusts the outflow accordingly. The bottom one adjusts the value of the stock accordingly to make outflow equal inflow. The top one adjusts the value of the flow accordingly to make the stock equal to X target. You appreciate that? Again, I'm not asking you to give a round of applause for it, although you're welcome to do that. But it's just, yeah, okay, you grok it. Okay, great. Now, you notice that these are not automatically the same. So in order for this to be the same, X target is just inflow times delay. That's what makes these equal. If you define X target to be the same as fixed inflow times the delay, then that will basically lead to a completely the same mathematical situation. It's just we can frame it in either way, as goal seeking in the stock or as goal seeking in the outflow. And they lead to basically the same result. So here we could frame it in terms of an inflow of 10 and a delay of 20. And here the outflow will equal the inflow, and X will go to delay times 10, which is 200. Alternatively, we could frame it in terms of here a target being 200, and so that's 10 times the delay, 20, and the value of the stock will seek out this value of 200 for the target. In either case, X goes to 200. That's when it's in balance, and the outflow here will go to 10. Up here, the outflow will go to what? Or the flow will go to what? When this stock equals 200, what would this flow be? 0. It'll be 0. It'll be in balance. This flow is just the sum of outflow and inflow down here. That's all it is. These are two ways to frame a first order delay. It wants to follow a target in terms of the value of the stock. like a perception adjusts to a new reality with a certain delay. Our ability to judge where our car is on the road adjusts with a certain delay when we've got snow coming down. Our sense of how well we've mastered the material adjusts slowly as we get marked or what have you. We learn from mistakes. Here, we can frame it in terms of adjusting stock, or here in terms of outflow and inflow, okay? These will be the building blocks that will accompany us all through this class. Agent-based modeling, we're going to be reasoning about it this way some, and in terms of discrete event modeling, it will be useful as well. Okay, so let me give the summary of the first order delays, okay? They're regulated by a negative feedback loop. They're associated with the negative feedback, regardless of whether we frame them as at the top or down here. There's a negative feedback. You could see the minus in front of the x2 would increase in x2. Here will lead to ripple through effect that will lower the flow into x2, thereby pushing back on that. Or if the system is in balance, if we increase x2, for example, so it's larger than x target, the flow will flow out and will bring x2 back into alignment. With the bottom one, here, if the stock is increased, the outflow will be larger. It'll be less than the inflow, greater than the inflow. The value of the stock will be larger. The outflow will be greater than the inflow. It'll drain the stock down and pull it back into balance. So there's a negative feedback here. It's pulling it towards stability. Do you appreciate that? Okay. The flow out involves a typically constant coefficient, and we can either phrase it as a division by some amount of time you spent in that stock, or you can phrase it as a multiplication by a rate of leaving that stock. Your chance of leaving that stock is independent of how long you've been in that stock. If you've been in that stock for 10 years, your chance of leaving in the next month is the same as if you just entered the stock. It's well mixed. It doesn't care how long you've been there. It's memoryless, as we say it. Okay? That's an important feature. These things are going to be really valuable with agent-based modeling in a few weeks, okay, as well. Given a constant inflow, the equilibrium is the value of the delay, the mean time in the stock, times the value of the inflow. In epidemiology, they deal with this a lot. We have a mean time with disease, we have an incidence rate I, and the prevalence of disease is the incidence rate times the mean time with disease, for example, in equilibrium. Or if you have a chance period in time of leaving the stock, the equilibrium is I over alpha. Okay, that's the equilibrium which inflow equals outflow. Why? Because the value of the outflow is the value of the stock times alpha, and the value of the stock times alpha is just I over alpha times alpha at equilibrium, or I. And that's when inflow equals alpha. Okay. Summary of first order delays. Are we okay with that? Okay. Seeing no riot, I will continue. Any questions on these? This is the single most important building block of system dynamics models. And when you see a system dynamics model, typically you can immediately recognize, oh, there's all these first order delays. It's just a bunch of first order delays with this innovation or this thing different. These are the building blocks out of which we'll build the more general model. Okay. I said further first order delays associated with the negative feedback. We could specify a first order delay either in terms of a target, something where the value of the stock is following a target, or something where it wants to keep the outflow equal to the inflow. The top one, where it's following the target, there's only an inflow, so we don't really talk about it there. But for this bottom one, it wants the inflow to equal the outflow and adjust the stock accordingly. The top one, it wants to make the value of the stock equal to the target and adjust the flow accordingly. Okay. Great. Okay. So that's good. I think I'll skip competing risks here, except to say that when we have two outflows, there's some additional components to it that are interesting, and I'll leave it for interested students to explore. But in the meantime, I would like to use this time to build up a little model. So I'd like you to call up your AnyLogics, and we're going to build up a system where we have this target follower, okay? Where we're following this target. Hopefully it's something that should be familiar for you, but it's something that I want to reinforce. Okay, so here we go. This, and I will transition over to my AnyLogic here. Okay. So start up your AnyLogics. And what I'm going to do is to go create a new model. And the model that we create is going to be first order delay, much like this one, except there's only going to be one flow into it, okay? The flow into it is going to be governed, the value of that flow is going to be governed by the difference between the target and the value of the stock. So I'm going to say new model. Here we go. And this is going to be called target following first order delay. Okay, there we go. And its time units will be years. Now, one or two students last time had some problems with the model displaying properly. And I discovered that there was a discrepancy. They hadn't put in this time unit, and yet they had used years as for other things. And as a result, it was simulating the model based on seconds. But meanwhile, there were delays of years for things, and it led to very, very slow behavior, for example, where the behavior did not change materially over the time frame seen because the time frame was in seconds, and it took years to adjust. Okay, so I'm gonna close this original guy, and we'll go over to this new one. Okay. Okay. So we just created this model, and now we will go drag into the model from this palette, drag in a stock, and we will call the stock X, or we'll call it, yeah, X, sure. And now we will drag in a flow, and that flow will flow into X, okay? This is going to be called adjustment, okay? Next, we will create a dynamic variable. This dynamic variable will be called gap. Give me the gap between actually, and I'm going to rename this. I'm going to call, I'm sorry, folks, I just clicked there. To make it clear, I'm going to call this perceived X. So it's a perception of some X. Okay, how did I do that? I just went to here and I changed it. You'll notice, by the way, that this is saying d perceived X dt equals adjustment. So the rate of change of perceived X is just the value of the flow in. The stocks integrate flows. The rate of change of this, if adjustment is 0, the stock won't be changing at all. If the adjustment is 10 people per year, the stock could be going up by 10 people per year. Okay, this is perceived X. The value of the gap will be dictated by perceived X, but it's different from some actual X. So I'm going to drag over here another parameter in, or a parameter in, and this is going to be called, ladies and gentlemen, anyone want to guess? It could be, yeah, let's call it target. Yeah, that's good. Target. I like that. Okay, one more time. I'd like student suggestions. So instead of calling it perceived X, guess what? I'm going to call it perceived. So I have target, and then or perception. That's what we're going to do. Perception. So that's my perception of the target. So much of life, ladies and gentlemen, has to do with following perceptions, trying to chase them, trying to target them. Okay, so here's the perception, and here's the target. We regulate our activities as a society, as a government, in terms of our individual behavior, often to achieve certain outcomes. And so we're trying to perceive, are what we're doing leading to those outcomes? And if not, we adjust accordingly. And our perception tracks the situation, but with a delay. So we're going to have a target, and it's going to contribute to the gap. And it's going to be the gap between target and perception, okay? So the gap is going to be, is it target minus perception or perception minus target? We'll make it target minus perception. It's how much bigger the target is than our perception of it, okay? Target minus perception is going to be the gap. Oh my gosh, I just changed its name rather than its value. Sorry. Here we go. This is the gap. There you are. The value of the gap is target minus perception. So the bigger the target is off, the bigger there'll be an obvious discrepancy between what we thought was the case and what's actually the case. Next. So we're going to be, so as this system adjusts, what is it going to be doing to gap? It's going to be trying to do what to it? Shrink it, to make it 0. So the adjustment is going to be based on the gap, but then it's going to be based on a perception delay. Perception delay. This is going to be the time between when something is the case and how long on average it takes us to perceive it. And here we go. So perception delay. We're going to make the default value of perception delay be 10. Let's make it more than, yeah, sure, 10 time units. Yeah. Okay. And finally, what is the value of the adjustment? What's the formula for adjustment? Perception delay is 10. The gap is target minus perception. And what's the value for adjustment? What's the formula for that? Anyone? Adjustment, sorry, the value of adjustment is it's got to refer to the gap because we're going to adjust accordingly, divided by the perception delay. Let's talk about this. Oh, perception delay. So the bigger the gap, what is this going to mean for the inflow? So if the target is way above our original perception of it, that's going to give us a signal in terms of the gap that our perception needs to rise to follow the target. If the target is way below our perception, the gap will be negative and we'll end up draining this. But we'll do so only at a certain rate. Only at a certain speed will we adjust our perception. It's given by perception delay. Let's suppose, ladies and gentlemen, that the perception delay was huge. How quickly would our perception follow the target? If we had a huge perception delay, how quickly would our perception adjust to follow the target? Very slowly, because perception delay is going to be really big, and so gap divided by it is going to be really small. And so our perception will adjust, but only very slowly. Suppose perception delay is really small. How quickly will our perception adjust? Much faster, right? The gap between the target and perception will be picked up, and it will lead to a quite big change to perception to bring it in line with the target. Okay, so let's go run this thing. Here we go. Run. Boom. Okay. Here we go. So we'll go run this. Okay, here we go. So time is a ticking. Oh, wait, we made the target 0. Oh man, let's sorry folks, let's make the target something meaningful. Let's make the target 100. Okay? in general, for parameters, you can specify them in the in the scenarios. So a parameter specifies an assumption. It communicates that assumption. If it's in main, it communicates it to the model from the experiment. So here, for each experiment we have, we could specify a different value for target. Here, we're going to run this. Boom. Okay, the target is going to be 100. What do you think is going to happen? If the perception starts at 0, what's going to happen initially? It's going to start growing very rapidly. Yeah, because there's a big gap between the target and the perception. So here it's growing very rapidly. Let's go graph it out, right? There it is. It's growing rapidly. And what value will it be approaching? The value of the target. Now, let's suppose we were to knock perception down. Whoa. So here we go. If we were to knock perception down, knock it down to, or put it up too high, 200, what's going to happen now? What's going to happen now? Goes up to 200. It's going to come back down to follow the target. Why is that? If perception is 200, the gap is going to be very negative, which is going to lower the value of the perception to follow the target. And by changing the value of the target, we could change this value. So I'm going to change the target to be 50. And watch this. It's going to come down and approach 50, right? Is it ever going to get fully to 50? No, it'll just approach it exponentially. Now I'm going to make this target 500. 500. What's going to happen as a result? Stock value go up. Why does it go up? Because the gap is very large, and so the gap drives this adjustment. Suppose I were to, by contrast, enhance the perception delay, or not enhance it, I'll make it 100. I'm going to make the perception delay 100, okay? Now I'm going to adjust the value of the target down to from 500 to 100, and it's going to decrease. But you notice how it decreases. With a very large perception delay, it decreases very slowly down, okay? Ladies and gentlemen, the other phase of first order delays is this sort of target follower. We are going to build something more interesting yet out of these models. You will see first order delays all around. They are legion. You'll see a model composed of it. But next time, ladies and gentlemen, we are going to create nonlinear models. And nonlinear models will have much more interesting behaviors yet. It's very important to build these intuitions with models which are easy to understand. You can even solve them. Next time, we're going to go into models where the whole is greater than the sum of the parts. The behavior of the model as a whole is very different, and they have not just one equilibrium, but multiple equilibria. They can behave in unexpected ways, in very different ways, depending on the parameter values, or depending on the initial state. They will be composed of lots of pieces of first order delays, but there's going to be some nonlinear component in them. A component where we have a multiplication of two state variables. That will allow us to simulate the spread of rumors, the spread of infection. It will allow us to simulate innovation and its transmission over the population. In short, it will open up for us a lot of additional lines of modeling using these sort of aggregate models. And first order delays will accompany us all through. And most importantly, this basic reasoning about if a stock is growing, it means inflow is greater than outflow. If a stock is constant, it means inflow equals outflow, and so on. That will be a key way of sort of parsing out what's going on in this model. We're going to be working on that next time. In the meantime, we have the weekend. Okay. I was going to distribute, but I held off, partly out of sympathy, a take-home exercise for this week. Given yesterday's assignment due date, I didn't want to add insult to injury. Okay, so There will be one, however, posted for work over the weekend for Tuesday that I'd like you to try. In the meantime, enjoy the weekend, enjoy the good warm weather while it lasts. Okay? Thank you. Yeah.
What was the perception delay for?
Sorry?
The perception delay for?
Yeah, you're saying what job does it for?
Yeah.
So basically, it captures the fact that, with respect to perception delay, it captures the fact that we often will have a system that tracks something, but it takes different amounts of time for it to sort of adjust to the new reality. Okay. So
But
maybe
what you do in the model?
sorry.
What you do in the model?
What? Oh, so like